And so after this wonderful introduction to samples from everywhere in the solar system, we're going to cover the solar system from the inside out. And we'll move on to our next talk, which is going to be given by Francois Tissot from Caltech. And Francois is going to talk about linking the protosolar disk with the inner solar system.
Thank you. Can everyone hear me? Yes, I see nods. Excellent. Thank you for being here this morning, and I'll try to link the protosolar disk with the inner solar system as we discussed. So just to orient ourselves in a grander scheme, we're here today. About 13 billion years ago, the galaxy formed, and there is 9 billion years of galactic chemical evolution that happens until the solar system forms. In comparison, that's a very, very short event. It takes only 10 to 50 million years to go from gas and dust to planets as we know them. And we are trying to study this exact process standing here today. So we don't have too many options, but we have two main routes that we can use. One is that we can look at objects in formation somewhere else and very far away. And that is what astronomy does. And it has yielded very interesting results. This is one image, one very famous image from the ALMA array showing a planetary system being born. What you're looking at, so this is 50 astronomical units here. You have a protostar in the center. You have a disk of gas and dust surrounding it. And what you see are gaps, potentially where planets are forming, but there's a question mark here. And then rings of gas and dust. Everything I'm going to discuss after this is within what the arrow shows at the center, the protostar. It's the inner disk, 50 AU. This is 12 AU. We're looking at the Earth, Mars, so a couple AUs from our sun. And the question is, of course, is this how our solar system formed? To answer the question to our solar system, we have only one option. We need to look at meteorites. There are remnants of the formation process. And so the very brief outline, I'm going to give a very, very brief primer on meteorites, but I expect everyone knows that already. And then we're going to look at nucleosynthetic anomalies and how they allow us to trace the processes and the mixing and everything that happens in the disk. We're going to look at what we think we know as of today, and then discuss the missing building blocks of terrestrial planets and why that really requires that we go and get some inner sample return missions. So very briefly, we have two main types of meteorites. Some sample differentiated planetesimals or planets that were broken up. We get stony meteorites that we think represent the crust or the mantles of those planets. We have iron meteorites that we think represent the cores of those differentiated bodies. And sometimes we're lucky and we get something that's in between. Maybe it's at the core mantle boundary. Maybe it's mixing during the impact. But those are the main categories of objects that we can study. The second type is sediment, space sediments. So we call them chondrites. We call them chondrites because they're full of little chondrules. And we call chondrules chondrules because it means little sphere. So this is really an exercise in hiding your ignorance. But inside chondrites, we have two things. We have, or three things, but two main things. One are the refractory inclusions that I highlight here. When we date them, those are the oldest things that we get, oldest ages that we can measure in a solar system material. And then we have those chondrules. And there is about a 2 million year time period between these objects. Yet they have coalesced into a single material. So these objects must have been floating in space and then accreted into a sediment and not be processed for millions of years. All right, so with this out of the way, what are nucleosynthetic anomalies and why am I going to talk about this for most of the talk? Let me know if this is not clear, because if it's not clear, the rest of the talk is not going to be clear. Here we're looking at the abundance of isotopes relative to a standard. So one means that we're looking at the standard. All the abundance is exactly the same for each isotope. We have measured the standard compared to itself. When we measure a natural sample, it will look something like this. Compared to the standard, the isotopic abundances will be linearly correlated to their mass. It's what we call mass-dependent fractionation. And this happens when you do any physico-chemical process. It can be alteration, it can be evaporation, melting, condensation, anything that you do in the solar system will have some sort of mass-dependent fractionation associated with it. Sometimes, however, like this little guy here, one isotope or a couple of isotopes will not follow the mass dependency. We call that an isotope anomaly. And we need to characterize exactly what this anomaly comes from before we can tell that it's nucleosynthetic. So the thing we do very often is that we normalize, we impose a ratio. Here we impose the 47-49 ratio for the titanium isotopes. We fix it to the terrestrial value. And this is essentially a rotation in that space, meaning that everything goes flat except the anomaly that remains. That's how we make those measurements. And these measurements are very delicate to make. You can only make them on Earth-based laboratory. You can't fly the instrument. There is absolutely no way this would work. So we end up with this thing, epsilon titanium. This is the isotopic anomaly. If we can prove that this is not due to radioactive decay or cosmic ray exposure or some particle capture, then very likely the only thing that remains, and we can look at it and prove it further, is that it's a nucleosynthetic process that has created the anomaly. Something about the generation of the signal in the star. So, if that is clear, then we can move on. Anomalies are a developing field. If we start from the 60s, at the time, Cameron said, well, the solar nebula was very hot. Everything must have been vaporized and homogeneized, and that's what we call the hot solar nebula, where the composition of the solar system is absolutely the same everywhere. You can see where I'm going with this. Of course, this is not correct when you look at the finer scale. So in the 60s and 70s, people started to measure isotopic anomalies in first the noble gases, but then very quickly in refractory inclusions, they started to see anomalies in things like calcium and titanium, very clear departures. They started to look for what are the carriers of these anomalies. They took a sample, added a bunch of acid, very reactive acid on it, so you can think of this as like a Breaking Bad approach to trying to find your carrier. And then it looked like the sample was digested entirely, but when they dried it down, there was an unbreakable residue that remained. This is the discovery of pre-solar grains. Those are nanodiamonds here. Very refractory phases that no amount of chemistry on Earth will destroy. And these are very exotic isotopic compositions. From those times until today, there's just been a steady stream of discovery of nucleosynthetic anomaly in everything at the larger and larger scale. So today we can resolve nucleosynthetic anomalies even in bulk meteorites, which at some time was considered impossible. And this is how we know what we know about the structure of the solar system that I'm going to discuss. So very briefly, what are nucleosynthetic anomalies useful for? They tell us about the sources, the stellar sources of the material that makes up the solar system. We can use them to infer things about the architecture of the solar system or the genetic link between planetary bodies and even the disk transport and mixing. Let's look at the first point, the stellar sources to the solar system. So I'm taking here molybdenum as an example. This is a ternary diagram between the S process, the slow neutron capture process, the R process, the rapid neutron capture process, and the P process. So 92 and 94, they're P process isotope. 100 molybdenum is an R process isotope, and these are created by a mixture of S and R in the solar system. And the way we can distinguish these processes is that when we do this internal normalization exercise that I just showed you, if you focus on the top panel here, we normalize to 96, 98, and the R process will look like this VW pattern. Now the S process will look like just a single W pattern. It's very characteristic. If you measure them, you can't get them confused. The P process is even simpler. You only have an anomaly in 92 and 94. Everything else is flat. So we can, looking at a material, we can tell which type of star participated to the composition of that material. Clear diagnostic power. Now, how does that tie into the structure of the solar system? We're going to look at a lot of plots like this and see what they mean. So this is, again, epsilon titanium, epsilon chromium, very small deviation on the parts per 10,000 from the composition of the Earth. 0, 0 is terrestrial material. And the thing I want to emphasize before I show the data is that to move in that space, the only process that can do that is mixing between end members. You can do anything you want to the sample, heat it up, melt it, evaporate it. It doesn't matter. It's not going to move. The only thing you can do is mix materials, and then you can move on that plot. With that being said, this is how decades of research have shaped the distribution of materials. We have, I mean, you don't have to be an isotope cosmochemist to see that we have two groups of material, one at the top right here, one at the bottom left here. The Earth is here, the Moon is right next to it, enstatite chondrite, ordinary chondrites, some differentiated planetesimals, and here the carbonaceous chondrites. This has been called the isotopic dichotomy. You might have heard that term. In one of these groups is very water poor, very volatile poor. It's what we think is inner solar system, and mainly is high temperature materials. The other one, so this is non-carbonaceous. The carbonaceous group is very rich in water and volatiles. It's lower temperature materials. The fact that there is no continuum between the two means that these two things were separated somehow. Maybe they were separated in space, maybe they were separated in time, but they were not allowed to mix extensively. So when we look at the time of accretion after CAI for chondrites and achondrites, in red will be the non-carbonaceous, in blue will be the carbonaceous moving forward. We see, and molybdenum here is just used as a proxy for this dichotomy of isotopes, we see that the two coexisted. There are both non-carbonaceous and carbonaceous material formed at the same time, yet they didn't mix, so it's not a separation in time, it has to be a separation in space. How do you achieve something like this? If we go back to astronomy, we can get a hint. Remember the gaps in the disk that are being dug. The main hypothesis that has been proposed is that the early formation of Jupiter within 1 million year of the solar system formation has separated and then kept separated these two reservoirs from one another. It's not the only proposal that is out there. It is one of the favored one, but there are alternative scenarios, something like the migration of a snow line that could explain the formation of these two reservoirs. In this model by Lichtenberg, the snow line moves outward and initially some material starts to form along it, and then it recedes as the disk is calming down and you have a second reservoir that forms. Here there is a bit of an implied time difference between the two, but it's difficult to resolve, so the proposal still holds. The other way you can do it is you can form them at the same time in different places. This is a model by Alessandro Morbidelli where we're looking here at heliocentric distance, temperature, so this is the temperature profile of the disk. At about 1300 degrees, this is where silicates are going to condense, so you're going to condense the rocky material, very dry. That's where Morbidelli puts the non-carbonaceous material. At the very same time, much further out, you have the snow line, and that's where he condenses the carbonaceous material that are very volatile rich. This is what we can summarize as like pressure bumps hypothesis. Now, oh no, that is the only figure that really needed to work. All right, that is not looking good. I'm going to explain that on the blackboard then. There are two main ways that, or maybe, yeah, I'm not sure why that figure didn't make it through. It's okay, I can explain on the board. We were looking at how the isotopic heterogeneity was preserved. It's step by step. It's okay, I can draw it. It shouldn't look like that at all. So just ignore the board for a minute. That board, I mean. So how is it preserved is a different question from how did the heterogeneity arise. And the way we think about it is there are two different types of models. So you have the forming disk, and there is material falling onto the disk and the star during the active accretion time period. The first type of model is called inheritance model. The isotopic heterogeneity we see today in the disk is inherited from the heterogeneity of the cloud that's collapsing. So you have an early infalling material that's going to be CAI-like, like the refractory inclusions, and that goes first into the disk. So the disk at time 0 is more like the refractory inclusions. But as time goes on, the infold material changes, and now you start to infold NC material onto the disk. So far out, the CAI material has moved out. Far in, you have the non-carbonaceous material, and then if you let the two mix, you get the carbonaceous chondrite types. So that's the inheritance or the infold model. The second one is the exact opposite. It's called the unmixing model. You start with a completely homogeneous cloud and completely homogeneous disk, and it has the CI chondrite composition, so like Bennu and Ryugu. But then in the disk, there are temperature gradients, there's thermal processing happening. Some of the carriers of the anomalies will be thermally evaporated, thermally labile, some are refractory. And so through the processing in the disk, this CI material is going to split into what becomes the NC and what becomes the CC material. Now, there are strengths and weaknesses to both of these. The major weakness of the unmixing model is that even though the anomalies are consistently seen across geochemical behavior, lithophile elements, siderophile elements, volatile elements, refractory elements, here you require that the carriers of all these anomalies are magically selected and transported. So that is really the main weakness, and that is the main strength of the counterpart process, which is you just have to have two original reservoirs, and then you let them mix. Yes, so I think this is the PowerPoint self-censoring, because I was not supposed to show anything that was not published, and this is not published. Now, why would the infold composition change over time? We have to remember that this is a physical process, and we have clues about what's going on. So this is a stellar nursery. We have very strong stellar explosions going on, giant stars with very rapid lifetimes, very short lifetimes. They explode, they inject new material into the molecular cloud, and then we have future planetary systems forming in those very dense regions at the top of those pillars. So we're injecting new material onto forming solar systems. Thank you. Astronomical observations show us that, that this is a very likely scenario, actually. So what you're looking at here is, this is the ALMA system, the same image that I showed earlier for reference. And those colored regions, these are showing the relative speed of the gas parcels as seen through observation. So this is 1 kilometer per second movement here, 13 kilometers per second here. So this parcel of gas is moving 10 times faster than this one, and they're just moving past each other. You can deliver material with an isotopic composition that is different from the protoplanetary disk onto the protoplanetary disk. And this happens at every stage of the disk formation. So you should actually expect that the disk will have heterogeneity imparted and imposed onto it. Now let's move into what does that mean for the inner solar system. So we have building blocks of planets, and we're trying to understand how we make terrestrial planets. We said that the non-carbonaceous material is high temperature, the carbonaceous material is lower temperature. The Earth is right here, and so it's not a big leap to say, well, if the Earth looks most like those materials, maybe these are the main building blocks, and then you add a little bit of something that's volatile and water-rich, and that's the water source for the Earth. That's very simplistic, but it's very appealing to do. And you can just say the Earth is some percent of NC material, some residual percent of CC material. So if you take enstatite chondrites that are right here, the Earth would be 90% enstatite and like 10% CI. Or you can take uralites or angrites, and then it's more like 50-50 or something like this. I'm doing it in a very hand-wavy fashion, but you can do it much more robustly. So if we look here at isotopic anomalies, for a number of different elements. The Earth, by definition, is at 0. The chondrites and the different meteorites that we have access to, we can measure these anomalies for them. We get those kind of spider diagrams of anomalies. Some are very far enriched above the Earth composition. Some are depleted compared to the Earth. And you can see the enstatite chondrites are in green here, very close to the Earth. If you play the game of what can I mix together to get the composition of the Earth, unsurprisingly, the best fit is the one that uses a lot of enstatite because it's already very close to the composition of the Earth. This is a game that has been played for decades. People played that game with elemental ratios. Now they're playing it with isotopic compositions. You can play it using chondrites or achondrites. I didn't list everyone here, but there's many, many, many papers doing this. The main limitation is, of course, the answer you get is a function of the input you consider. If you consider more or less element, it's going to work more or less well, and then it assumes that you have all the possible building blocks in your hand. So if you only consider chondrites, the Earth has to be enstatite-like. If you consider achondrites, then the Earth and Mars both require something like 50% of angrite, which is a pretty small family of meteorites. There's only 30-something samples from them. It wasn't supposed to be or thought to be a very important family of meteorites, but they look very much like the Earth. This second argument actually is very much in line with the current thinking that you make planets from differentiated planetesimals, not from chondrites, which are the leftover of planetary formation. The second thing you can do is you can look at the accretion history of terrestrial planets with anomalies. Lithophile elements accumulate in the mantle and nothing happens to them. So something delivered early weighs as much as something delivered late. This is the mass fraction accreted. Those are just cumulative density function. But anything that is siderophile, that will tend to go into the core, the early accreted material will tend to go into the core more than the late accreted material. So you don't record that much of the chromium in the first 20% of accretion. You don't record any of the nickel in the mantle in the first half of the accretion. Molybdenum really records in the mantle only the very last part of what's happening. And ruthenium is just the very late veneer because everything else will have been stripped into the core. So with something like this, you can essentially reconstruct a history of the accretion of a planetary body, which is a very powerful approach. But again, it's limited by what do we have as input. So here the conclusion is again that you use mostly enstatite to make the Earth. And so we're going to get back to this. Do we have an exhaustive collection of building blocks? I'm just going to very briefly touch on to the volatiles, but I'm going to leave most of it for next talk. Recently, people have discovered anomalies in volatile elements, or moderative volatile elements. This is zinc isotopes. Again, the non-carbonaceous material, the carbonaceous material. The Earth is the green point. And so you can see that the Earth is kind of in between. 30% of the zinc of the Earth comes from CC material, which is not that much. Mars, 0% of the zinc comes from CC material. Mars does not have a CC contribution compared to the Earth. So very clearly different accretion histories for the two bodies, and we can tell that just from these kind of measurements. The big question is, of course, what happens with Venus, which is 50% of the mass of the inner solar system, and Mercury. I'm going to skip on the similarity between the Earth and the Moon, but in a nutshell, they are the most identical bodies that we have measured, like completely unresolvable differences in almost every system. And so either Theia, the proto-impactor, was like the Earth to begin with, or the two completely equilibrated, which is an open question. Now, I mentioned that there are missing building blocks. In this space, everything is nice and tight. We can create the Earth by mixing NC and CC material. I'm going to replace chromium with zirconium, another element that has nucleosynthetic anomalies, and now try to make the Earth by mixing things. You can't, because it's an N member, and there's nothing pointing this way, so the Earth is 100% Earth. That's the conclusion that we can draw from this plot. Or it's 100% enstatite chondrites and just we have some analytical difficulty. So we're going to crush the enstatite chondrite thing very quickly. Isotopically, it's true. The Earth is very close to enstatite. Chemically, major elements, enstatite chondrites are here, magnesium, silicon, aluminum, silicon. The Earth is the furthest you can be from enstatite chondrites. Moderately volatile element, this is a volatile over refractory element, volatile over refractory. The Earth is here, enstatite chondrites are right here. There's order of magnitude between the two. So chemically, it doesn't work. You can't make the Earth out of enstatite chondrites. You have to make the Earth out of something that is very high temperature material. So the way people are thinking about this problem right now is that there must be something here. It's just we haven't gotten any sample of it. And so we're missing a major building blocks. Now you could be saying, well, that's just one dimension where we're missing something. So it's not. We have lots and lots of isotopic spaces where the Earth is an end member and there's something missing to manage to explain the composition of the Earth. So the question is the unsampled reservoir, this missing reservoir, the inner solar system material? And it's super easy to answer. We just need to get a piece of Venus, and then we will know the answer. Now, why would we be missing this material? This is what we have access to. Most of our samples come from asteroids. Asteroids come from the asteroid belt. We have lots and lots of meteorites, but that's a very small sampling. And then we also get some Martian meteorites. But the assumption is that what we have is representative, which is very unlikely. It's very unlikely that the asteroid belt contains all the solar system materials, and that if it did, we got a sample of each of them in our collection. So we really need to go and get the samples ourselves. Now, what key question would we address? Trying to summarize things here. The main one is really, what is the composition of the inner solar system? Isotopically, of course, but also chemically. A lot hinges on that. So isotopically, is it homogeneous and uniform? That would readily explain the problem of the Earth looking exactly like the Moon, which is a big problem for the community. The other question is there a missing end member that is lacking in our collection? And again, this is readily addressed by return emissions. Now, the thing I'm personally most interested in is what was the volatile accretion history of Venus and Mercury? Did they start with the same amount of volatiles and moderately volatiles, completely different amounts? This can be only answered by this kind of missions. And then we have this problem that the way we understand the composition of the Earth today almost entirely relies on the assumption that the building blocks of the Earth are chondritic, which might not be correct, because the Earth might have formed from higher temperature material, and then the MGSI ratio is not something that we can extrapolate that way. So this is a big open question. So I'll leave you with just a couple of conclusions, but if you need to remember anything from this talk, isotopic anomalies are the way that we can reconstruct the structure and the evolution of the solar system, looking at meteorites and return samples. And the field has made tremendous progress over the last 20 years. 20 years ago, people didn't know that there were anomalies in bulk meteorites. Now we're using these anomalies to tell things about the structure of the solar system. But the real future of that field is going to be in return samples, especially the inner solar system. Thank you.